Good afternoon, everybody. So glad to see you guys. And my name is Mengyun Tang, and Jiqiang is my co-speaker at this time.
Hi, guys.
Today, we are going to talk about our recent research progress about artificial intelligence security. And the title is Model Robustness While Hard Data Privacy. Before I started, I want to introduce our team first. We are from Tencent Zhuque Lab of Tencent Platform Department. And Tencent Security Platform Department has been with Tencent for 16 years and dedicated to the protection of QQ, WeChat, Tencent Games, and some other critical products. Our interests include Tencent account security, AI security, anti-fraud, anti-scamming, insurance detection, and mobile app security, and so on. Tencent Zhuque Lab was founded in 2019 by Tencent Security Platform Department, focusing on red teaming and AI security research. Okay, let's come back to the topic. In this talk, we want to discuss the existing challenges of AI at first and discuss the relationship between AI and security, including the vulnerabilities of AI components and new attacks targeting on AI systems and some other things. And then we will introduce the background and the motivations of this work, including some fundamental concepts such as adversarial attacks, adversarial training, and model privacy attacks. After that, we are willing to introduce how to steal data from model gradient, illustrate our experiments, and discuss how to defend such attacks. At the end, we will conclude this talk and present some other interesting studies. I think everyone here has heard how incredible, powerful, and successful AI is. Many different tasks that could not be solved with software before are now solvable, thanks to deep learning and neural networks and gradient descent. All of those technologies that are working really well, and we call them AI. Absolutely, the time has come for AI. This is possible because several developments that are currently coinciding. First, the computing power of computer processors has increased rapidly. Second, huge amounts of data are available today from the cloud and high mobile bandwidth. This is important because AI systems are particularly useful when it comes to identifying patterns in large amounts of the data. Besides, software developers are now able to write programs that work in a similar way to the human brain. Artificial intelligence has long since found its way into our everyday lives. For example, 50-16% of jamming already use voice assistants, such as Amazon's Alexa or Apple's Siri. Smartphones are able to recognize whether somebody is traveling by foot or in a car. And thanks to intelligent algorithms, Facebook, Twitter, and the like offer us exactly the information that interests us. So, how to build an AI system? Before an AI system is being used, it will go through many processes. Typically, if an AI engineer starts to develop an AI system, the first thing is to collect the data. Usually, for different application scenarios, there may be different data types, such as images, videos, text, and so on. Data preparation is typically important because it significantly determines the robustness of the AI model. So, in this process, engineers must carefully to check the data and select the bad ones. After that, AI engineers use the data to train a deep neural network and then evaluate the qualities of the trained model. That is to use the data out of the training set to test the recall, precision, or some other evaluation criteria of the model. Once the criteria satisfies the requirement, the model will be deployed. The most common way is to deploy the AI model as a cloud service. It provides it provides users with an inference API, which takes users' data in and then outputs the prediction results of the AI model, just like a black box. However, each process of developing an AI system may be attacked by attackers. So let's think about the relationship between AI and security. I think on the one hand, security challenges AI. The first challenge is that the components of AI systems may contain vulnerabilities. AI systems usually contains many fundamental components, such as deep learning frameworks, TensorFlow, Caffe, PyTorch, and so on, and the accelerate frameworks such as TensorRT. Software packages, most of AI algorithms written by Python and use a lot of Python packages such as OpenCV, NumPy, Pandas, and so on. All of those components may contain vulnerabilities. For example, bug hunters had found 37 vulnerabilities of TensorFlow. Once those vulnerabilities are adopted by attackers, the AI systems will be vulnerable to be attacked. Besides, there have emerged a lot of attacks targeting AI systems. As we know, data, algorithm, and model are three most significant components in AI, but unfortunately, all of them have been proven to be vulnerable. First, the data used for training an AI model may be attacked by data poisoning attack. In most cases, a large amount of data is typically required to train the model. So, AI engineers cannot check each data during the data preparation. This makes attackers have opportunities to modify a part of the data and makes the trained model with a hidden backdoor. When this backdoor model takes a normal data in, it outputs normal results, but when it takes a specially modified data in, it will output a certain incorrect result. Second, previous work has pointed that AI algorithms based on deep neural networks are vulnerable to be fooled by adversarial examples. And an adversarial example is an example that we apply some small perturbations on, making the prediction of the neural network change to another label. And for most cases, such modification on an image usually cannot be notified by human eyes. Besides, as you know, various AI services are available on the cloud. We send the data in, it outputs the prediction results. For example, image classification. We send an image to querying the AI service. Then it outputs the label and its corresponding confidence. However, based on that, attackers may utilize the outputs of multiple queries as a target loss to retrain a new model. And the model is similar to the one provided by the AI service, so that they can achieve the purpose of model stealing. The last but not the least, the risk of AI abuse is also a significant security problem. Let's think about that. What will happen when we use AI in a wrong way? I think it may be a weapon of the underground industry. For example, deepfake, an AI-based technology. Giving a few pieces of somebody's voice, it can imitate his or her voice to make a fake call. Or giving a photo of a target person, it can swap the target face to a video. Then the underground industry can use this method to bypass the face anti-spoofing. Besides capture, AI also has been an effective tool to solve captures. So AI is a double-edged sword. It makes our lives more convenient, but also brings some security problems. On the other hand, AI also enables security. For example, we use AI to steal WAF protection rules. Traditional methods to achieve that highly depend on the experiment experience. Typically, those methods observe WAF response by sending attack payloads and then infer the rules through multiple attempts. This process is very label-intensive and time-consuming. With AI technologies, we can use pre-trained model to link the security experience hidden in the payloads and to utilize attention mechanisms to locate the part of the payloads that contributes to the detection results. After that, we can use a recommendation model to rank the probabilities of the candidate characters. It does not require excessive manual invention and can run on a larger scale. Okay, let's Jiqiang to continue the talk.
Thanks, Mengyun. Hello guys, I'm back. Let me introduce the background and the motivation of our work. As we know, machine learning algorithms accept inputs as numeric vectors. Adversarial attack refers to an attack method in which the attacker perturbs the input of the model, resulting in wrong prediction. The perturbed input data is called adversarial examples. As the image shows, here, starting with the image of a panda, the attackers add small perturbations to the original image, which results in the model labeling this image as a cocktail shaker with high confidence. The process of adding these perturbations is easy, as the formula shows. We emphasize that the adversarial attack has affected the various AI tasks, including image classification, object detection, auto speech recognition, and so on. As the image shows, the audio is added small perturbations, but the translation of the video audio is quite different. Before adding the perturbations and the translation it was the best of times. It was the worst of times. But after adding some perturbation, the translation will become it is a truth and universally acknowledged that a single. Unfortunately, almost all existing models are vulnerable to this attack, which can be regarded as a natural defect of machine learning models. Fight fair with fair. Adversarial training, in which a network is trained on adversarial examples, is one of the most promising ways to defend against adversarial attacks. Simply put, adversarial training introduces adversarial examples as part of training data. The problem can be formulated as solving a min-max optimization problem during training a model, with the inner maximization generating adversarial examples by maximizing the classification loss, and the outer minimization finding model parameters by minimizing the loss on adversarial examples, which generated from the inner maximization. As the figures show, before when the model is trained by traditional method, when we import adversarial examples, the model will make a wrong prediction. But after we use adversarial training method, the model can make a correct prediction on an adversarial example. It means that the robustness of the model has been improved. On the other hand, in machine learning field, an often overlooked danger within machine learning is the research on privacy attacks against machine learning systems. Here, we introduce two classic privacy attacks. The first is called the membership inference attack. The attacker aims to determine whether a data point is part of training data just by observing model's output. Membership inference can cause security and privacy concerns in cases where the target model has been trained on sensitive information. What's more, the attackers may not only want to know whether the piece of data point is in the training site, but also wants to reconstruct the underlying data, giving just a black box access to a classifier. That is the second attack, called model inversion attack. In this attack, the attackers are given only the label or names and access to a model, and that returns a class confidence score. Then the corresponding data can be recovered by the attackers through continuous input and output. As the image shows, if the attacker gave a label named bird, the training data, the bird in training data will be recovered with high confidence. Now back to our work. In this our presentation, we focused on how to steal data from model gradients. It's a new type of privacy attack. First, we give a brief introduction to the gradient, which is fundamental to machine learning. During training a model, we input the training data to the model and calculate the difference between the current output and the expected output by loss function. Then we back forward the loss and calculate the gradient, which stores all the partial derivative information of a multivariable function to update the parameters of the model like the GIF. This is a gradient. This is a process of gradient descent. Put in simply, we can take the gradient as a meaningless matrix. But we want to steal data from the gradient. Before we introduce our attack methodology, I will explain our threat model. As we know, exchanging gradients is widely used in multi-node machine learning systems, such as federated learning. People believe that the model trained in this way can protect data privacy because the training data will not be leaked by gradient exchange. However, we will prove that if the attacker gets the model gradients, he will steal or reconstruct the data from it. So the exchanging gradient provides a false sense of security, especially when adopting adversarial training to enhance model robustness. It's an interesting finding. Look, here is a demo. We initialize a piece of random data and imported it into robust model and standard model to get gradient. We continuously reduce the distance between the current gradient and the leaked gradient through iterations, so that the random data is optimized to look very similar to the original input. From the GIF, we can say comparing the gradient produced by the standard model and the robust model. It can be clear to see that the robust model is more vulnerable and the reconstructed data based on it is much clearer. Thus, we claim that the model robustness will have a negative impact on data privacy in some cases. To prove that we did not come to this conclusion by accident, we select multiple model architectures and data sets. The detailed experimental parameters are listed in the table. For evaluation metrics, we use PSNR, MSE, and FMSE. The first two metrics are used to measure the quality of data reconstruction, and the third is used to measure the distance between the reconstructed data and the original data on the model prediction. The reconstructions are shown in this slide. The first row represents the original input image. The second row is the reconstruction from standard model gradient, and the last row is the reconstruction from robust model gradient. We can clearly see that the visual quality in the third row is better than the second row, and the conclusion is always hold regardless of model architectures or datasets. For standard model, the reconstructed data appears to have more mosaic, and some position information of the image is lost. For example, the location of the bird in the second row is lost. On the contrary, for robust model, the reconstruction is much clearer, and the location of object in image is maintained. From the evaluation metrics, the results tell us that adversarial training poses a more serious risk of privacy leakage. To illustrate that this attack is valid for all phases of model training, we save different states of the models and test the attack. The blue line and the orange line represent the natural and robust accuracy under adversarial training, respectively, and the green and yellow line represent the natural and robust accuracy under standard training, respectively. The x-axis represents the number of training epochs, and the y-axis represents accuracy. The attack results for models with different training stages are shown below. With blue representing the quality of reconstruction based on adversarial gradient, and the orange representing the quality of reconstruction based on standard gradient. It can be clearly seen that the robust models are always more vulnerable regardless of training stages. On the other hand, we emphasize that the choice of the initial value of the target to be optimized will affect the efficiency and the effectiveness of the optimization. Thus, the quality of data reconstruction is related to the initialization value of random data. A good reconstruction stability can obtain a high-quality image regardless of the initial value. So we selected 10 random numbers as seeds for random data initialization and fix a gradient to attack. It can be seen that the reconstruction based on the gradient of the standard model has worse stability and is more sensitive to the initial value. In addition, it will also cause the loss of location information, as shown in the fourth row. On the contrary, a better stability can be obtained under a robust model. This confirms the privacy risk brought by adversarial training from another angle. We also try to find a trade-off between robustness and privacy. So we set different robustness parameters to get the robust models, and found that as the robustness increases, the quality of data recovery is better. But when the robustness reaches a threshold, the quality of recovery will decrease rapidly. Last but not least, we discussed several, we will give some possible defenses. The first is differential privacy, which adds elaborate noise to the gradient so that to cover the information contained in it. However, adding noise will reduce the accuracy of the model, and how to find a balance is a challenge problem. The second is to use cryptographic technique to encrypt the update. Even if the hacker hijacks the gradient information, the original input cannot be recovered from the encrypted information. But encrypting millions of parameters during training a model will bring unaffordable computation overhead. So it is unrealistic. The third possible defense is to combine standard training and adversarial training to design a privacy-preserving algorithm, which can not only enhance the robustness of the model to defend adversarial attacks, but also resist gradient leakage attack. But as so far, there's no related algorithms. So it will be our future work to design it. Finally, we have 4 conclusions. The first is security is still one of the biggest challenge in deploying AI systems. The second is that we list the 3 most significant security challenges of AI. The third is that training data of AI model can be stolen according to the gradient. And the last is that our ultimate goal is to build secure and trustworthy AI systems. Yeah, in the appendix, we list some other interesting study of ours. For example, steganography. The information hiding is one of the important ways to ensure data. We try to implement a case that image hiding in another image. And mosaic recovery. We use sec-to-sec model to restore mosaic text. And for AI sec metrics, we build a AI sec metrics to provide developers and users a better guidance on the security problems of AI systems. And for shredded document, the reconstruction of shredded text documents with matrix learning are designed, are proposed by us. Yeah. So we also looking forward to share more research progress with all you guys in the future. The above is all the content we shared this time. If you have any questions, please contact the relevant email address. Thank you guys. Bye.